Hello, 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 organic chemistry. Welcome to Unit 3. How exciting. We've made it this far. Welcome to Unit 3. Now, in our Unit 3, we're actually going to look at several different reactions. And starting from today for the rest of the semester, all we're going to look at are reactions, and then we're going to turn around and use them. And so our tests are going to follow the same process for the rest of this semester. We're going to have about a third mechanisms. So you'll notice in this unit with this first video, we are going to start with mechanisms always in our reactions. They explain how reactions work. They give us the rules to those reactions. And then our goal is to get to know those reactions so well, we can turn around and use them in synthesis. So we'll always start with mechanisms, and then we're going to end with synthesis. And then these reactions might also pop up in our roadmaps. We'll have at least one roadmap on every test as well. So we're looking at probably a third of our test mechanisms, a third of our test synthesis, and then we'll have a roadmap and one fill in the blanks. And our fill in the blanks is just gearing us up for synthesis. So this will comprise probably the other third of your exams. So this video, we're going to start number 1 with mechanisms. And I want to build on something that we've already learned. So I'm actually going to start both this video and the SM2 video with acids and bases. I've given some web links here since we're trying to go zero textbook, but of course I still love a handful of those textbooks. So if you've got them, definitely take a look at them. I've given some links here for radical halogenation as well as here. These are just a little bit more beefy. These are just a little bit more just kind of giving you the facts and the terms. So feel free to take a look at them, see if any of them are helpful. I do want to give a general disclaimer that radical halogenation, we are going to keep it very much on the surface. And we are not going to get super deep with it. So you want to be careful in your sources because this topic can get pretty deep, and we're going to get pretty deep into side products and all kinds of things that can happen. That is not the focus of our radical halogenation. We're simply going to give the basics of radical halogenation. So be careful here. We're going to keep it pretty much on the surface. Okay, so I just want to warn you when you start looking up things and you're looking at your radical halogenation that you don't panic and just start going down that rabbit hole. All right, so let's pose a question. Why do we even give a crap about radical halogenation? I'm going to pose a question from our last unit. I'm going to take a nice alkane. Let's mix it with what we've learned in Gen Chem is a strong base. We just learned in our last unit, Unit 2, not so strong. And then let's see if we can figure out what we're going to make here. And let's do exactly what we did in our acid-base section in Unit 2. Let's label everything. Let's figure out what's the acid, what's the base. And then let's look at this reaction. Is this really going to happen? Let's look at our pKa values. So I'm going to start with an alkane. If you want to look at your pKa table, that would be awesome. In general, our pKa of our alkanes is phenomenally high. You're going to find it's probably somewhere to the 50 to 60s range. And then our sodium hydroxide, we don't even need, so I'm going to take the extra step and I'm going to draw my structure. We don't even need our pKa table because look at those available electrons just right out there screaming, hey, I'm available. This is absolutely your base. Okay, you've got the negative sign there and you've got your available electrons right there. This is your base. By default, that means your alkane is your acid. So already you should be questioning me, Dr. A, are you kidding me? Look at that pKa. So just for funsies, let's actually draw what we would make, and then we're going to evaluate if this reaction would even happen. So if we've got an alkane, we've got a couple different options of hydrogen. Your pKa is not actually going to change much with these, so we can just choose any of them. I'm going to go ahead and draw my mechanism. That's what's going to help us draw our product. Okay. So what would we actually make? We would leave those electrons behind on our carbon. We would form that water. Oh, well, that's a fluffy bond. And then we would have our floater of sodium left behind. Okay, remember, you don't draw a line to that. That's ionic. Okay, so now let's put a pKa in there for water. Remember, our water we saw was 15.7 on our pKa table. Okay, I love it. So now, if I were to ask you as a test question, which way would our equilibrium lie? Oh, certainly this way. Our much higher pKa is with our alkane. In fact, look at that difference. And remember, these are log functions. So you have a difference of 16 to almost 60. In fact, it's so extreme, I could really hazard a guess to say you're not even going to go forward on that reaction. Okay, now let's put a couple comments here. Number one, on almost all of the MCAT preps I've seen, this is a common trick question. Okay, so we just gave that one away for free. You are not going to deprotonate an alkane, especially with something like sodium hydroxide. Any of our bases, you cannot deprotonate an alkane. They are the top of the pKa chain. They will always win. You will always favor your alkane, so it's a total trick question. And then I want to do a quick reminder, what kind of mechanism are we looking at here? This was our first mechanism, and it is polar. Do you notice we're moving 2 electrons at a time, and we're using a regular arrow to do that? So it doesn't mean we're totally screwed when it comes to alkanes, especially if you look at the world we live in. Our petroleum industry is a massive feedstock, not just for the gasoline in your car, but actually for a lot of our alkane precursors. So are we totally screwed if we can't really do many reactions with an alkane? Well, not so much. Okay, let's add some sheets of paper here. I'm going to town on my screen. I apologize for that. I just need to have my keyboard up if I'm going to add pages. So let's see if we can get that to happen. Okay, so are we totally screwed? No, but this is a great place to start our Unit 3 because, check it out, alkanes, let's look at their bond energies. Let's look at something like a CC bond or a CH bond. And we need to break that bond. We need a solid 99 kilojoules. That's actually quite a bit. To break a carbon-carbon bond, we're right around 83 kilojoules. That makes our alkanes notoriously unreactive. Except for 2 common reactions. Now, are there some maybe rare and very specific sassy reactions out there with an alkane? I'm sure there are, but there are actually only 2 pretty common reactions for an alkane. This is a great place to start synthesis because we only have 2 options. And wait for it, number 1 is a combustion reaction. We learn those in Gen Chem. And no matter what's your alkane, you can light that sucker on fire and you will always make CO2 and water. This is great when you're thinking about a fuel source. Not so great if you're thinking about synthesis. So if you want to actually make something from an alkane, you are completely screwed because the only thing you're going to make when you light it on fire is CO2 and water. So if you want anything other than CO2 and water, not going to happen. So we are really not actually going to focus on that one. We're going to leave that one for Gen Chem 1 and 2. You see those quite a bit. In fact, we're going to slim it down to number 2. And number 2 is called, you guessed it, a radical halogenation. Now, our radical halogenations are so much fun. They are really a nice classic example of a radical mechanism instead of a polar. And remember, I promised you 3 types of mechanisms this semester. We have a polar, we have a radical, and organometallic. So we're going to focus this video on a radical mechanism. So radicals, let's give a couple rules before we actually start. Radical mechanisms are completely different than our polar mechanisms. What's awesome is that they always follow the same pattern. So even if it seems like you're copying your notes when you write your mechanism for me, I would like that because there is only one way that this mechanism is going to happen. They do follow that pattern, and that pattern is that mechanism. And then our radical reactions are only 1 electron at a time. Thus the radical, they are not 2, which is polar. So our arrows look different. They have only 1 end instead of 2. So they look like little fish hooks. You can always tell a radical mechanism versus a polar mechanism by the arrows that are used. Awesome. So let's get a little bit more specific then. What does a radical halogenation look like? Well, let's take a general alkane. We really can do these with any alkane. I'm just going to use propane to start, just to keep it kind of simplified. And as we're using our radical propane, okay, we're going to keep in mind our reaction conditions. And what are they? So what do you actually need for radical halogenation? What does that mean? Well, we have 4 common halogens. We have fluorine, iodine, chlorine, and bromine. Radical halogenation works the best with chlorine and bromine. Fluorine is a little bit too reactive. Iodine, a little bit not as reactive. So they actually are opposite. The fluorine is too much, so it's really not a viable reaction. The iodine, not so much. So with iodine, it tends to be a polar mechanism. So we're going to keep it to our 2 common halogens, chlorine and bromine. And now you can mix those up forever, and not really anything will happen unless you have something in there that's going to initiate the process. For radical halogenation, the cheapest, easiest, and most common is actually light. So we commonly abbreviate light as our Planck's constant in frequency. If you remember from your Gen Chem, that equation. So this is our common abbreviation for a photon of light. And you have to have that in your radical halogenation, okay? So you have to have both. And then what are you going to make? And then we'll draw the mechanism. So what you're going to do is actually substitute that halogen on your alkane. And what we've made now is an alkyl halide. And why is this so important? And why is this the first reaction in this unit? Okay, shut the front door, just wait for it. When we take a look at our actual bond energies now, if we're looking at a carbon-chlorine bond, we have just dropped in energy to only 81 kilojoules. If we are looking at a carbon-bromine bond, shut the front door, we have dropped all the way to to 68 kilojoules, meaning we are going to take our alkane and make it reactive towards other reactions. So yippee, this is about to be a starting reaction for us. We're going to start here, and then our alkyl halides, we're going to branch out into 4 more reactions in this unit. They are called an SN2, an SN1, an E1, and an E2, because now we've got a bond that's easier to break. The easiest bond to break is typically the one that breaks. So this is awesome. So first, let's make an alkyl halide, and then in our next series of videos, we're going to take our alkyl halide and react it. Let's use it. Let's do something with it. Okay, so let's draw the mechanism. How do you understand how a reaction works? You draw the mechanism. So with our alkane, let's take chlorine first, since that's the example that we gave. You typically see chlorine and light. And then I'm going to redraw our products. And we'll draw a mechanism for each one. We'll draw our mechanism separate. Okay, I'm going to put brackets to kind of signify I'm going to have some transition states in there. Okay, the first thing that happens is not the alkane, it is the chlorine. And this is why I said nothing is really going to happen until you have that light. So we're going to take a photon of light, and it is just the right energy to break this bond. Only what it does in that bond is it breaks it even Steven. It's called a homolytic cleavage. It does not break that bond to one side or the other. You literally break it even. So what you've just done to your chlorine is form two radicals. Now, do we have a charge on there? No. Look at the periodic table for chlorine. How many electrons should it have around it? It should have 7. It has 7. Now, that doesn't mean it's not crazy reactive right now. It just means there's no charge. So we've just made our free radicals. This process using light, this first step is called an initiation. Okay, so let me ask a deep question. What if you don't want this reaction to happen? How do you block it? You block the light. Keep this reagent mixture in the dark. Have you ever gone to the grocery store and noticed that there are bottles that you buy that are dark? All right, for funsies, let's stop and tell a story. When you go buy wine, what do the bottles look like? Are they see-through or are they dark? They're typically dark. Guess what they're blocking? They are blocking light to block the initiation of that process to start to have your wine start to decompose. When you go to buy booze like beer, aren't they all in dark bottles? The process of skunking beer is actually radical. So you keep your beer in a dark bottle or a can, so you block the initiation step, and that is what blocks the skunking of your beer. Except one popular bottle of beer, and I heard this in a seminar, gosh, about 15 years ago. It's been a while now. Except one brand of beer is still in a colorless bottle or a clear bottle. Does anybody know what that is? Corona. Way back in the day, they decided that it was actually cheaper and easier to train you to do something to your beer versus change their entire bottling process into a dark bottle versus a light bottle. And then it just grew and it became habit and it's a thing. So what do you do to Corona that you don't do to other beer? You add a lime. So they're not even blocking the skunking process. They're just teaching you to cover it up with a lime. Isn't that fun? Okay, let's get back to business. All right, once we have our free radicals, they are actually crazy reactive. And they are reactive enough now to react with our alkane. So we have to have that first step, otherwise nothing is going to happen. Now here's the funky part. Let's track our electrons. We have 2 electrons in that bond between carbon and hydrogen. We only need 2 electrons per bond. So we're going to do something called a hydrogen abstraction. Hey, no sir. Sorry, y'all. Our hydrogen abstraction is our next step in this process. And what we're going to do is take 1 electron from chlorine, 1 electron from hydrogen, and form a bond. And then what happens to this little guy? It gets left behind. So let's draw that product. My sassy puppers in the background. There's a hummingbird out here. Pretty sure he is just, oh, that's just not at all the product. I got sidetracked by the dog. All right, so what are we actually making? Well, first of all, we just formed a bond between hydrogen and chlorine. So we just made HCl. And then let's track our electrons. Didn't we leave behind an electron right here? Absolutely. Okay, this step is called propagation. Now, this is where radical processes can go crazy. You have a very reactive radical here. This radical can react with another chlorine radical. It can react with HCl. It can react with another propane. It can react all over the place. It is now very reactive. Now, in our class, we're just going to show the productive one. So let's take our radical down here, and I'm just going to flip my structure, and let's react it with our other chlorine radical. But this is one of those places that when you're reading about radical halogenation, it can really get deep fast because there's a lot of byproducts there. Okay, what did we just form then? We just formed our alkyl halide, and we now have used up all of our radicals. That is called a termination. Oh, my pen got fluffy there. Let's fix that. This is called termination. So I'm going to mark the brackets like that, okay? So we've just ended our mechanism. Now let's just go back and count. We generated 2 radicals of chlorine. We used 1 here, and we generated HCl, so that is a byproduct. You're going to make some strong acid there. And then the second one we used to make the alkyl halide. So if you do these reactions, you do build up HCl, and then you end up making your alkyl halide. Now, all radical reactions will have that process where there's an initiation, propagation, and a termination. So when you're drawing these mechanisms, make sure you have all 3. Your initiation, the most common initiation, is usually light, but you can have other initiators. Benzoyl peroxide is a good initiator. You ever wonder why that's in all kinds of stuff? All right, there's lots of ways to initiate. Peroxides are also good initiators. Light hits them and they can kick off all kinds of radical reactions. So there are ways to initiate. Propagate is usually, for us, it's going to be our alkyl radical. And then termination is when you use up all of your radicals. Okay, so now if you've noticed, wait a second, we made 2 products. What's the difference? All right, in the middle of that mechanism, when we had our chlorine radicals, we just kind of chose this hydrogen. But these radicals are so sassy. They can bump into this hydrogen also. So that is where the second product comes from. Let's just draw that little bit in between there. Okay. And then this is where we would make the other product, chlorine in the middle. Now we can draw the full mechanism for that, but I'm actually about to turn around and draw that for bromine. So let me go ahead and do the same mechanism for bromine. And then actually we better stop this video. It's getting a little long. So we're going to have a second video with radical halogenation, and